Hello, this is WeiRen. Now I'm presenting gate drivers, techniques, and solutions for GaN neutral HEMTs in high-frequency applications. So here's the agenda. First is the introduction. Here we'll talk about the benefits of gallium nitride material, challenges when it comes to applications, and the differences of driving considerations. Then we will move on to anomaly of gallium nitride technology and the driving challenges. After that, we will check some commercial gate drivers for gallium nitride HEMTs. Also, the switching simulation of commercial gallium nitride HEMTs are performed. Finally, the conclusion. So why do we choose gallium nitride materials as power electronic devices? Because of the superior electrical properties. From the table, we could see that for the wide bandgap materials such as silicon carbide and gallium nitride, the electron saturation velocity is 1.5 times more than that of silicon MOSFET. And for the electron mobility in the two-dimensional electron gas channel, the electron mobility is higher than silicon MOSFET. That suggests gallium nitride materials could have a larger current for power applications. Also, the critical electrical field of wide bandgap materials are 10 times of silicon MOSFET. It's better for power device to have a larger breakdown voltage so that we could operate at a very high voltage operation. And last is the thermal conductivity of the gallium nitride. Though it's lower than silicon at silicon carbide, but the device could be packaged into a flip chip or have a change structure. So in that way, it could also achieve a higher heat dissipation. But one drawback for the gallium nitride HEMT is that it's normally under zero bias voltage. The two-dimensional electron gas is intrinsically accumulated. The electron gas will drift once there's a bias on the drains or the source terminal. But for these properties, it's not desired in the circuit design. The complexity of and source is thus increased, and the power is still given to turn the device off. So the power efficiency is decreased as well. To reach a anomaly of operation, many methods are proposed, such as recessed gate, Florian treatment, or P-GaN gate capping layer, and the cascade structure. The P-GaN gate capping layer and the cascade structure to reach anomaly of gallium nitride are available commercially. For the cascade structures, a low voltage silicon MOSFET is introduced to an depletion mode GaN HEMT. The turn-on and off of the gallium nitride HEMT is decided by the gate terminal of the silicon MOSFET. In that way, we could reach anomaly of operation. The other method is adding a P-GaN layer on the gate region so that the conduction band is raised and the two-dimensional electron gas channel is blocked under the zero bias. And the voltage is required to make the on again to reach anomaly of operation. The comparisons between two methods are shown in the table. For cascade gallium nitride HEMT, because it inherits silicon MOSFET's properties so that threshold voltage is larger than that of P-GaN HEMT, but also the recovery charge is larger than that of P-GaN HEMT. P-GaN HEMT has no recovery charge. We could predict that the high-frequency performance is better. However, the main drawback is that the threshold voltage of P-GaN HEMT is very low. It's about 1 to 2 volt. This raises more concerns during driving situation. Manufacturers produce anomaly of HEMTs, and the method is listed on table. The HEMTs from transforms and GaN systems are selected for the simulation in this paper. The next part is the driving challenges for EMO HEMT. Here, EMO HEMT means another HEMT achieve anomaly of operation by adding a P-GaN capping layer. Because the driving cascade GaN is actually driving a low voltage silicon MOSFET, So a standard driver designed for silicon MOSFET is compatible with cascade HEMT. But for IMO HEMT, because the threshold voltage is low, thus it's easily turned on by voltage draining. When the first turn on or off happens, it might cause permanent damage to the devices. Also, since GaN HEMTs could switching at a very high slew rate, the reading amplitude is thus larger. One method is to add a gate resistor to adjust the slew rate, but the trade-off between the performance and the reliability should be a concern. Another method is to prevent spurious turn-on and turn-off is to give a negative gate voltage during the off state, so that even the reading occurs, the voltage would not exceed the threshold voltage. But here arises another problem, which is when you applying bias voltage and the device is off, the current collapse phenomenon increases circuit complexity and higher power losses are the potential threats for the application. Moreover, if we have to apply negative voltage during off-state, then it makes no difference whether it's the enhancement mode HEMT or depletion mode HEMT. So this page shows the commercial gate drivers designed for GaN HEMTs. We could see that because the GaN could operate at very high currents, so the ability of drivers to sink and source currents should also be higher. Also, for the isolated drivers like Infineon, Silicon Labs, TI, and analog devices, the common mode transient immunity values has to be high enough to follow up the high slew rate of gallium nitride. HEMT. For non-isolated drivers, a faster response isolator is needed to avoid common mode noise. Also, Infineon and Panasonic gate drivers allows negative gate voltage, as mentioned in the previous session, to prevent a spurious turn-on. Then is the simulation part. We simulated high transient switching results of enhancement mode HEMT and cascade HEMT. For the enhancement mode HEMT, we choose HEMT fabricated by the GaN systems, and for cascade HEMT, we choose HEMT from the transformer. A half-bridge circuit is simulated. Given inverse signal of VG1 and VG2, the high-side device and low-side device is switched on and off simultaneously. Then we extract the voltage of switch points and the gate side of low-side HEMT, also the gate current of the low-side HEMT. The simulation parameters are listed in the table. The off-state gate voltage is 0 volt for both HEMTs, and the on-state gate voltage is 6 volt for IMO HEMT and 12 volt for cascade HEMT. The drain voltage of a high-side HEMT VDD is 400 volt. Two different rise and fall times simulated, 5 nanosecond and 10 nanosecond. The slew rate is thus 80 volts per nanosecond and 40 volts per nanosecond. Here is the simulation results of rise and fall time of 10 nanoseconds. From the results, we could see that for the cascade HEMT, the reading amplitude is much higher than that of enhancement mode HEMT, and the reading frequency of the IMO HEMT is higher than that of cascade HEMT. Then we turn on the device faster. The rise and fall time is 5 nanoseconds. We could observe that the reading amplitude for IMO HEMT is larger than the switching at low speed. But for the cascade HEMT, there is not much difference between switch at 10 nanoseconds or 5 nanoseconds. It's not corresponds to the rest time. So from the simulation results, we could first see the major differences in reading amplitude. The cascade HEMT has a higher reading amplitude than IMO HEMT. The results could be explained from the gate capacitance difference. The gate capacitance of cascade HEMT is 2 times larger than IMO HEMT, but because cascade HEMT has a higher threshold voltage, so even the reading amplitude is large, it is not large enough to cause a spurious turn-on for the cascade HEMT. Also, because restricted by the silicon MOSFET limitation, whether a device is switching at a high slew rate or low slew rate, the results are almost the same. That is because the device couldn't follow up the transient speech, but for the emo GaN HEMT, it could respond to a higher transient speech. But for the emo HEMT, even is capable of switching at a high speed, but due to the limitation of the low threshold voltage, an external resistor is required to prevent the device from switching too fast, like cause the range amplitude larger than the threshold voltage. In the simulation, when switching at the 5 nanosecond for in rest time, get resistors lower than 5 ohm will cause the spurious turn-on of emo HEMT. So in the summary, this paper reviews the driving strategy for emo GaN HEMT. Because of the low threshold voltage, the driving principle is different from silicon MOSFET and cascade HEMT. Emo HEMTs are capable of high slew rate operation, but the slew rate control is needed to prevent spurious turn-on. Also, a simulation of comparisons of emo HEMT and cascade HEMT is performed. It suggests that emo HEMT is preferred for the high frequency operation. Thanks for your listening.